Okay, so this is session 3 for lesson 6. This is the last session for this lesson. So again, the learning target for this is basically this. It's we want you to recognize that when you have a number in a certain place, if you move it to the left, it'll be 10 times greater than it was. Or if you take that number and move it to the right, it'll be 1/10 or divided by 10 and become smaller. So that's basically, like I said, the main idea of this lesson. So for a warm up, I've got this for us. So we've got, we're going to write these 3 different decimals in this next slide. We have 300ths. We need to show a number that's 10 times as great as 300ths and one that's 1/10 of 300ths. So let's start off with our first number. All right, so here is the number that's 300ths. So again, just to illustrate, if we move it to the right, it'll become 1/10 of its size. If we move it to the left, it'll be 10 times as big as it was. So it's going to get bigger. So they want us to show a number that is 3 times as big. Well, there it is. That's 3/10. They want us to show a number that is 1/10 of 300ths, and that would give us 3,000ths. So again, moving your numbers to the right, make it smaller, move it to the left, makes it bigger, again by multiples of 10. All right. Next slide. All right, open up page 129. And you should see, all right, just a couple of grids up there at top. So, all right, shade the models at the right to show how the value of 400ths is related to the value of 4/10. Then write a division equation to represent the relationship. All right, for this one on the left, let's make this one, just write that right above there, 4/10. So 1 group of 10, 2 groups of 10, 3 groups of 10, 4 groups of 10. So that's 4/10 of one whole that one of these grids would represent. And then over here, we want to write 400ths. So 1, 2, 3, 4. So 4 out of those 100 or 400ths is that. So over here, basically they're talking about this. Again, when we're moving that 4 one place to the right, we're actually dividing by 10. So we can just write it like an equation right here. So 4/10 divided by 10 equals 400ths, just like that. And on to the next slide. All right, for this one, Kieran showed, and this is 800ths, this value right here, with the model below. What's wrong with Kieran's model? Well, if we look at this, notice how none of these little lines are actually marked off with anything. So there's all of these lines are breaking up 0 and 1 into 10 different parts. So each of these lines represents a 10th. So I'm just going to label these 6/10, 7/10, 8/10, 9/10, and 10/10 is 1. So I just have it like that. However, this is an answer in thousandths. It is 8,000ths. So what that's actually going to look like, and forgive me for not being able to write it accurately, but you're going to get the main idea. That means we need to take this 10th right here and break it up into 10 parts. And that would mean, I'll change the color here. This would actually be 800ths, because that would be even smaller. So she used her number line to represent 8/10, and this represents 8,000ths. It makes it even smaller. Okay. And that kind of answers the question. How could you change your model to show eight hundredths or eight hundredths? I shouldn't have written thousands here. Sorry, kids. Erase that. Even math teachers get it wrong sometimes. 800ths. There you go. Next up. All right, number 3. How's the value of the digit 8 in 1.8 compared to the value of 8 in 486? Well, let's write 486 on one side and 1.8 over here. So let's recognize this. We know this 8 is in the tenths place. We know this one is in the tens. So we're comparing the value of the 8 in both of these to see, well, we could say it 2 different ways, and we're going to talk about it 2 different ways. So the 8 that's in this, the 8 tenths, that's actually, since this is our tenths place here, that is 2 places away. So that means 8 tenths is 100 times bigger. For this one, you just put a space here, and this is the tens. This 8, and then we'll divide by 10. So 8 tenths is 100 times smaller. I should have wrote bigger over here, and I'll do that. So again, every place value you move is going to be 10 times bigger or smaller. In these cases, we're moving 2 spaces, so we've got to do 10 times 10, or divided by 10, which is 100. So they're 100 times different from one another. And it's pretty simple. That is always the case. Every place value you move is just 10. Just keep multiplying tens or dividing tens to get your answer. And let's turn the page. All right, number 4, an ant. Oh, this is an interesting question. Very long and drawn out, but it's worth it in the end. Although they don't give you much room to write. But this feels like a science problem, so I like it. An ant has a mass of 5 thousandths of a gram. That's right here. Ant, 5 thousandths of a gram. A small bee has a mass of 5 hundredths. A grasshopper has a mass, feels like the movie Bug's Life. Grasshopper has a mass of 5 grams. Okay. So write each measurement in the place value chart below. So our ant right here, that is, let's put 0.005. Our B is, it's a small b, because that matters, is 5 hundredths. Our grasshopper, which is the biggest of the 3, is 5 tenths. Okay. And as you can see right away, there's this pattern here, and you could probably figure out what they're going to ask us, but let's look at it down below. Part B, shade the models to compare the mass of the bee and the mass of the grasshopper. And then we've got them labeled here for us. So a bee is 5 hundredths. So just fill in 1, 2, 3, 4, 5. The grasshopper is 5 tenths. 1, 2 groups of 10, 3, 4, 5. So you can see that's half of a gram. Then write a sentence to describe the relationship between the 2 masses. Well, if our grasshopper is 5 grams, or 5 tenths, excuse me, and our bee is 5 tenths, we know that there is a relationship of 10 times between them. So your grasshopper, or the mass of grasshopper is 10 times the b. Or you could say it the other way around. You can see the b is the mass of the b is 1/10 of the grasshopper. They can go either way. They can flip either way. And part C, explain how many ants it would take to equal the mass of one grasshopper. That's actually not as difficult as it seems. You take that's your mass of an ant. And since thousands here for the ant and the grasshopper's the tenths, that's 1, 2, 2 away from each other. That's 2 hops. Aha, pun intended. So multiply that by 10 and by 10. Oops. So what that means is R5 is going to jump over 2. That is 0.5. So that is what that basically lets us know is that it's going to take 100 ants to get us to move those 2 place values or to equal each other. So it takes 100 ants to do that. Pretty interesting question. All right, finally, what's the number that has a value 10 times the value of 9 thousandths? So let's write down 9 thousandths, and we've done this so many times, you're probably already thinking, if you want it 10 times bigger, just move it 1 place value to the left, and that will give us 9 900ths. Again, just to wrap this up, the old style way of teaching decimals is to tell kids to move the decimal point. The modern way that we're doing it that's more effective is to explain and help you understand why moving the number is ultimately going to tell them the value of the numbers instead of just moving a dot here and there. Okay, your homework. More Excel, you love it. I do too. But this one you'll like this one. It's G11 compare decimals on the number line. And you'll basically plot the points of 2 decimals on it and have to say which one's larger. You can see this visually, and then it kind of makes sense as far as logic goes, as far as their size. So go to 70 to get full credit for that, and you can go further for extra bonuses.